Physics has always wrestled with gravity. For over a century, Einstein's general relativity has been our best description, a beautiful theory of curved spacetime. But it breaks down when united with quantum mechanics, leaving physicists searching for answers. Many ideas, from supergravity to string theory, have dominated research, but none have delivered proof. Now, an old idea is making a comeback: quadratic gravity. Proposed in the 1970s by Kellogg's Stella, it modified Einstein's equations to make quantum gravity work mathematically. But it predicted a ghost particle, something that shouldn't exist. So the theory was abandoned. Today, with new tools and perspectives, physicists are daring to revisit this ghostly theory, hoping it might finally reveal gravity's quantum secrets. Quadratic gravity wasn't undone by a lack of elegance or mathematical rigor. Its downfall was physical, rooted in the very particles it predicted. The equations describe not just the familiar graviton, but also a harmless scalar and a problematic ghost particle with negative energy. In quantum physics, negative energy is a recipe for chaos, leading to runaway energy creation and negative probabilities. It's like withdrawing money and watching your balance go up, something we never observe. Because of these insurmountable problems, physicists abandoned quadratic gravity, turning instead to alternatives like string theory. But as new models struggled, some began to wonder if the verdict on ghosts had been too hasty. The recent interest in quadratic gravity isn't due to a sudden acceptance of negative probabilities. New arguments suggest the ghost might not be as dangerous as once thought. John Donoghue and Gabriel Menezes argue that the ghost's instability is its saving grace. The ghost decays almost instantaneously, vanishing before causing any problematic interactions. It exists only for a fleeting moment, too short to break quantum mechanics rules. This idea is part of a broader re-evaluation of handling exotic entities. Physicists propose modifying quantum probability rules to make the ghost's contributions benign. This controversial move could change foundational quantum field theory rules. But it opens up the possibility that our old interpretation was too rigid. Another idea is that the ghost might cause tiny, microscopic violations of causality. These violations would be so small and fleeting that they would average out, leaving large-scale causality intact. This suggests that cause and effect might be an emergent property, not a fundamental law. These theoretical breakthroughs are supported by new mathematical proofs. A 2024 paper showed ghost fields can form stable, normal mass-bound states. Research shows quadratic gravity is asymptotically free, meaning gravity weakens at high energies. This prevents mathematical breakdowns, suggesting quadratic gravity may be a consistent theory of quantum gravity. If quadratic gravity is a viable theory, it could reshape our understanding of the universe. One of its most exciting links is to cosmic inflation, the rapid expansion just after the Big Bang. The theory predicts a new scalar particle, which physicist Alexei Starobinsky identified as a natural candidate for the inflaton. His model, based on quadratic gravity, remains one of the best fits to our cosmological data. It also predicts primordial gravitational waves ripples in spacetime from the early universe. These waves may be too faint for current detectors, but could be found by future experiments. Quadratic gravity might even help solve the hierarchy problem, why gravity is so much weaker than other forces. Once left for dead, quadratic gravity is now inspiring new ideas in the search for quantum gravity. Its ghostly comeback reminds us: in physics, even haunted houses are worth exploring again.